So this is hopefully not too difficult of a one. Imagine that you're standing on the edge of a cliff and you throw a ball, 3 balls, all the same mass, perhaps something like that, with the same speed, but in different directions. When you throw up, when you throw straight sideways, and when you throw down. So which one ends up at the ground with the fastest speed? Give you a minute to think about that one. Okay. So, believe it or not, the idea here is that this is a conservation of energy question, isn't it? Which is that that's my magic equation I use for all these things. Idea being K initial plus U sub G initial equals K final plus U sub G final. So it starts off with some kinetic energy and plus a whole bunch of gravitational potential energy, ends up with a whole bunch more kinetic energy and 0 final energy. So it just gets converted. So, 1/2 mv initial squared plus mgh equals 1/2 mv final squared. So all it's at, so it's just saying that in both cases, in all 3 cases, it doesn't matter what the direction of the initial velocity was. What matters is that vi was the same in all 3 cases. It won't be true that they'll land at the same time. I think that the first one to hit the ground is going to be A, and then B, and then C. But in terms of what speed they hit with, all it has to do with is how much the vertical height changed and what the initial speed was. Any questions on that before we get going? Do we have another one? I'm in the mood for these. Let's do another one. You're such an active class already, but hockey puck on a frictionless surface going horizontally hits a frictionless incline. If you can imagine it, it's initially going up 4 meters per second. The incline goes up to a height of 1 meter. Does it make it to the top of the hill, yes or no? Just yes or no question. I think you might need to do a little work to figure out the answer to that, or you could use your gut feeling, I guess. But give me a minute. Okay, yeah, so that's actually what I got as well. I'll show you how I did it. So I've been playing with these little poppers things that you're going to be playing with in practicals this week. Idea is you do some work on them to transform them. They store this elastic energy, and then they pop up. So you're going to be trying to compute how much work you do to make them like this. You cock the popper. I don't know who came up with these words, honestly, but they're kind of, well, anyway, they're kind of embarrassing to say. And then the question is how much when it transforms into gravitational potential energy, how high does it fly up? So you'll be measuring that. With this one, I'm going to, again, just compare energies. So it starts off with, I guess, kinetic initial is equal to 1/2 m times v initial squared. I don't actually know what m was, so let's just leave it as a variable. We could say it's equal to 1/2 m times 4 squared, so it's equal to, I guess, 8m, right? Whatever m is, if it's in kilograms, then 8 times m will give you the initial kinetic energy in joules. And then we could compare that, I guess. So the way it's going to work is it's going to have some initial kinetic energy, K initial, plus UG initial, which is 0, is going to be K final, which will be less, plus UG final, which will be up here, right? So it's going to be, so I think that the K final is equal to the K initial minus UG final. And UG final is equal to mg times h. So it's m times 9.8 times 1. So it's 9.8 m. 9.8 m. So K final is equal to the K initial 8m minus the UG final 9.8. Oh yeah, well that's right. So you can't have negative 1.8 m. No, you can't do it. Like, you can't have negative kinetic energy. So anyway, that's why it doesn't reach to the top, right? It doesn't get there. Yes, question?
Can we make the assumption that at the top it stopped? Like it's not moving forward?
It wouldn't get, it has to do more than just stop. It has to somehow become negative. It has to go imaginary or something. Anyway, it doesn't, so what will happen in real life is that it will stop before it gets to 1 meter in the turnaround. And so we've imagined it to get up to the top of the hill, and we've come up with an unphysical result. So something about our imagination is wrong, and that's, the fact is, it didn't get there. Does that make sense? Sometimes that's what happens in physics. You do the answer and you get like the square root of a negative number or something like that, and you say, oh yeah, I've done some physics, there's something unphysical in my assumptions. I've assumed it made it to the top of the hill, but it doesn't. Okay. Somebody said something about, just very recently, will the test 2 be harder than test 1? I don't know. Not answering that question. We're going to try to make it fair and at the right level. Will practicals materials be in the test? Certainly Professor Seelfin has been helping us organize these practicals, is contributing the question, and so that yes. Right up into including the 7th practical that has these poppers, which goes right up until, if you have a Monday practical, I think it's actually on November 12th, the day before the test, so that's okay. Still have 24 hours to absorb it. And you can always read ahead as well. Here's a physics question. If I lifted a ball up, then brought it back down to its initial position, I would have done no work on the ball right. And so that's correct in a physics sense. I think in terms of work, I don't know, equal work for equal pay, like sort of a social definition of work, you should be getting paid at least $14 an hour to lift that ball up, but that's not what work means in physics. What work means in physics is it's this force times distance, and if the force and displacement are in the same direction, on the way up you do positive work. If they're in opposite directions, because you're kind of lowering it slowly while pushing upwards on it, then you're doing negative work, and those things cancel if it ends up at the same height. So yes. And this is again my famous UG chair question. Anyway, did I make a mistake if I want to do future physics? And no, you didn't. There's, I'd say, about half of my majors and specialists up in upper year courses started off in 131, 132. So it's, but you have to do calculus, of course. Okay, so I'm still stuck in this whole internal energy thing. It's the work done by kinetic friction. The idea is that sort of there's this macroscopic energy, 1/2 mv squared. If I have a basketball and it's flying along with some, or even better, this cart, which is sliding along with some initial v, that's macroscopic kinetic energy, because you say v is measurable, take a stopwatch and a ruler, you measure it, and then it stops, and it's converted that energy into probably the tiny little microscopic random motions of all the 10 to the 23 particles in the bottom of the blocks and in the table and all that. It's a conversion of kinetic to kinetic, but it's sort of macroscopic, being some big things, objects, to internal microscopic vibrations. Random vibrational and rotational motion of the atoms and molecules inside these objects, which we experience as temperature and heat, I guess. And this idea is that it's the work done by kinetic friction. And in fact, I probably should have put some absolute value signs on this, because the way I write this down, I always write it on the right-hand side of the equation as being something that's finally produced. And so it's thermal energy, which is positive, which is produced by the sliding kinetic friction. I'm going to do an example. So this is the way, there's actually two ways of doing this that I've seen in different textbooks. And actually it's interesting because Brian Wilson and I have differing ideas. I go with this textbook. This is exactly as I've always done it. But what Brian likes to do is he always thinks of the kinetic friction as being an external force. He likes to think of the system not including that thermal energy. And so if you think of kinetic friction as doing work, well, if the box is moving to the left, the kinetic friction force is to the right, the displacement and friction are in opposite directions, so that external work here would be negative. So instead of putting a positive thing on the right side, F case times D, you'd put a negative thing on the left side. Either way, you get the right answer, and whichever way you feel like doing it, it's fine with me. This is the way I suggest, because I like to think of that energy as still sort of there somehow, so it's there it is over on the right. The increase in internal thermal energy of the universe, I guess, if we include the system to be the floor in the box, due to kinetic friction. A couple of examples of this. So hopefully you can see it. Basic idea. A small box of mass m, right up here, is released from rest at initial height of 2 meters on a frictionless incline as shown. Doesn't give this angle, but it's frictionless, so that's okay. At the bottom of the ramp, it slides across a rough surface with a length of d equals 1 meter. And the coefficient of kinetic friction, it's either 2.5 times 10 to the minus 1 or 0.25, a quarter. And then it goes on a frictionless circular rise. At what height HF does the box stop on the circular rise? So one thing that's interesting about this is they don't give the angle of that first incline, and they also don't really tell you much about this curve. Well, they tell you it's circular, but they don't give you the radius or anything. So this is definitely a problem that you want to do with energy. And you have to, actually. You can't do this with kinematics because they don't give you enough information. So what I would do here is, again, do your initial sketch and your final sketch, sort of redraw it. Here's the mass on the incline. V initial is equal to 0. It's released from rest. It starts off with some h sub I. And then it goes across this surface there, which has a mu sub k is 0.25. It's going to go up the hill. And then finally, to sort of draw this again, it ends up here at some h final. This is the thing that we want. V final equals 0. That's because it gets to when does the box stop on the circular rise? And it's gone across this distance d, and it's lost some energy, delta U internal. So sometimes I draw these little squiggly lines to kind of make me think of the heat that gets left behind on the rough surface. I don't know. But anyway, you're going to use that equation, that delta U internal is equal to the F sub k kinetic friction force times D. Oops. So I'm going to move this to the left. And now do some more simplifying and diagramming and all that. So this is, again, one of these situations where you're going to need a force diagram in addition to an energy diagram. So for the force diagram, on the force diagram on the rough surface, that's where it's important, because that's where you're going to lose some of that thermal energy. So you've got mg down, you've got the normal force up, and you've got F sub k to the left. Again, A sub y equals 0, and so I think the normal force equals mg. And then if you want to do your energy boxes or whatever, the U sub g initial is up there. It starts at rest. And the very final, you've got your k final is also 0, plus your slightly less UG final. Whoops. Okay. We have to appoint someone as being the guy who yells at Harlow. I don't know if you want to, if I'm doing that again, just give me a, hey, you're off the screen. And then also this, am I off the screen yet? Delta U internal. Close. Okay, so it splits it up. So what I'm going to have is your M times G times H initial is equal to M times G times H final plus your F sub K times D. I think that's your basic equation. And this, another way of putting that is, let's just go down here, M times G times H initial is equal to mg H final plus mu sub K times M times G times D. So F sub K is equal to mu sub K times N. It's mu sub K times mg, right? See how I got that? And then, luckily, once again, the m's cancel because it wasn't given. And also look at even the g's cancel because they're in every single term. So it also works on Mars. And you get that H initial is equal to H final plus mu sub K times D. But now I've forgotten what I'm solving for. Oh yeah, HF. Solve for H sub F. And I get H sub F is equal to H sub I minus mu sub K times D, which is equal to 2 minus 0.25 times 1 meter, I think. I actually don't even need a calculator. HF equals 1.75 meters. Okay. A little less than initial height. Any questions about that one? Can we see it okay? Let me take a look. It's not brutal, but I'll definitely scan it. It's just so much easier for me to write on actual paper than to write on these tablets. I have another cool question, also using the same kind of thing. So this one doesn't really have any numbers in it. You've got a box of mass m. It starts sliding with an initial speed v up an incline at an angle of theta above the horizontal. So here's initial. Oop. Here it is. Here's your v. There's your theta. The coefficient of kinetic friction between the incline and the box, so this would be, I guess, the incline, and this is box B, is mu sub k. Okay, so it slides along and there's a screeching noise as it goes up. How far along the incline does the box go before it stops? So finally, what happens is it stops up here somewhere. V final equals 0, and it has traveled this distance x. So you can even sort of draw your xy axes like that, something like that. And here's your right angle, and here's your theta. Okay. So the whole idea here is that if this is, I guess, h initial equals 0, then it gets up to some H final. And so friction, again, creates thermal delta U internal as it slides. So we're going to need a force diagram, which is going to be a little bit more complicated, because now we've got the normal force of the incline on the the block, I guess. And then we've got gravity acting down, mg. And then we've got this friction force acting like that. And here we've got x up the hill and y like that. So, and it's accelerating back down the hill, a sub y, or sorry, a sub x, right? So, accelerates in negative x direction. So what that means actually is that a sub y equals 0. So the F net in the y direction is equal to 0. And that's the key to finding the normal force, actually. We need the normal force in these problems all the time in order to get this coefficient of, or this kinetic friction amount. So find the normal force. So we're going to have to do this component thingy on the gravity. Here's your theta. The thing that we care about is this negative mg in the y direction. So it's going to be adjacent over hypotenuse. It's going to be cosine of theta is equal to negative mg in the y component divided by mg. So the normal force F net in the y direction is going to be equal to normal minus mg cos theta. And this equals 0. So the normal force equals mg cos theta. So that's going to be useful later when we're doing all our energy stuff. So let's do the energy stuff. Okay. I still haven't even finished simplifying and diagramming. The basic job I'm going to do here is let's use energy. So you've got K initial, starts with some initial speed, plus, again, UG initial equals K final, it stops, plus UG final, it goes up a little bit, but also it has some internal energy that of this F sub K times X, I guess. So it's going to look like this. 1/2 mv squared plus 0 equals 0 plus mg h final plus F sub K times X, the distance it goes. And F sub K is equal to the normal force of I on B times mu sub K. So this thing goes into there. So F sub K is equal to mg, there's a mu sub K, and there's a cosine theta. So I get 1/2 m times v squared is equal to mg h final plus mu sub K mg cos theta times X. And the thing that I also want to do, I don't really care about HF, I just kind of introduced that. So I think though that I can kind of solve, if this is HF and this is X is the hypotenuse and this is theta down here, then we can, let's eliminate H sub F with, I guess that sine theta is H sub F over X. So H sub F is equal to X sine theta. So I end up with, and also, I think the m's cancel. My red pen is. So let's divide out the m's on both sides. We're almost done, everybody. v squared over 2 is equal to g times x sine theta, because that's the HF, plus mu sub k times g times cos theta times x. So I'm going to pull out, we're trying to solve for x, so let's pull out the factor of x. X times g sine theta plus g mu sub k cos theta. And end up with x is equal to v squared divided by 2 times g times sine theta plus mu sub k cos theta. So moving on, about 20 minutes left, I want to talk about collisions. So, Professor Wilson talked to you a lot about collisions in terms of momentum. The idea being that when two things smack into each other, there's a very small amount of time in which they are interacting. And there's big forces of one object on another during a collision. And so if there's any external forces during a collision, that could be having an impulse. It's usually a pretty small impulse because the delta t is so small. So that is why in collisions you normally see that the momentum gets conserved before and after. And so what we have is actually three kinds, every collision conserves momentum, but there's three kinds of collisions based on kinetic energy. So there's elastic. So right now I've got these two carts set up so that they are especially magnetically repelling each other. Have you ever played with magnets where they, anyway, the north and the norths are facing each other. It's kind of, you can't make them touch. Anyway, they're pushing. And it's kind of an elastic push. So what you do is if you put one stationary, don't move, and then you send the other one, it sort of transfers all of its momentum into the other one, the two equal masses. And so this is conserving kinetic energy. Whatever 1/2 mv squared this one has, it gets transferred all over to the other one, although it was moving there. So then you can, whoops. How are you? Got it. If you flip it around now, I can get the magnets to attract, and then the Velcro kicks in, and then they stick together. And this is a case that does not conserve kinetic energy. And in fact, if you think about it, if you do conserve momentum, then you've got mv, but then now the mass is doubled. So the final momentum is also mv, but now you've got 2m. So the speed goes down by a factor of 2. When you collide something, whatever speed it's going with, it slows down to half that speed. If you think about kinetic energy, 1/2 mv squared, if it now is double the mass, that makes the kinetic energy go up by a factor of 2, but now the speed went down by a factor of 1/2, which means the v squared went down by a quarter. So even though the mass went up, you actually have less kinetic energy. I don't know if you guys followed that. You see the difference? So mv, it just goes as v. So if you collide these two things, the mass doubled, so the v went down by a factor of 2. But mv squared, the idea is that the v again dropped by a factor of 2 because momentum is conserved, but the kinetic energy got lost somewhere. And so what happened is that there was energy that gets sucked up in the Velcro somehow. And you can hear it going rip when you pull it back off. Like all these little hooks and things store energy in the Velcro. So this is how we classify these things. So this is more of a kind of reading quiz, I think. So hopefully either you or your neighbor has read ahead. Two objects collide. So it's a collision. you can neglect external forces during the collision. If the collision is elastic, we mean that it conserves either A, momentum, B, kinetic energy, C, both, or D, neither. A minute. Going once. So it certainly conserves momentum. That's true. All collisions do conserve momentum. If external forces are negligible, right? And but in the case of an elastic collision, the kinetic energy is also the same before and after. So it's not storing any energy. Let's show another quick question here. Same sort of idea. What does inelastic mean? Again, these things aren't entirely obvious. They're just sort of definitions. So certainly since it's a collision, it conserves momentum. But the idea inelastic means that it does not conserve kinetic energy. And this is true for most collisions. Some energy is often lost. There also is a type of inelastic collision in which the kinetic energy is greater at the end. The total kinetic energy is greater at the end than at the beginning. These are called explosive collisions. What it usually means is that there must have been like a loaded spring or something that was in there, and then, or maybe some dynamite on someone's bumper or something like that. So you can imagine things gaining kinetic energy during a collision if it was triggered to release, I don't know, some stored spring energy or stored chemical energy. So this is the last question in this little series. Bit of different answer this time. Once again, two objects collide. All external forces on the objects are negligible. If the collision is totally inelastic, which is also a word in your chapter 7, what does that mean? A, momentum is not conserved. B, the final kinetic energy is 0. C, the objects stick together. Or D, one of the objects ends with 0 velocity. Okay, so this is good. A lot of people are reading ahead. To me, that's an entirely not obvious definition, but it turns out to be a sort of important special case. Often the things stick together and you can have this situation where you know that their final relative velocity becomes 0. And so that's a special case in physics and has some consequences. So, just for the last 10 minutes, I want to talk about elastic collisions. Because what's interesting about this is, let's for example, consider a head-on, perfectly elastic collision of a ball, some mass 1, m1, having initial velocity v1, with another ball that's initially at rest. And you can always go to a reference frame in which ball 2 is at rest. During the collision, there will be some stored potential, elastic potential energy or something. You can imagine those squishing out. But the idea is that at the end, that the kinetic energy final is equal to the kinetic energy initial. So if they have two final speeds, then you could treat this as basically being two equations and two unknowns. The two unknowns, so here's two equations that are separate and different. One is that you've got the mv's, and the other one is that you've got the mv squared. They look very similar, but the fact that those v's are squared make these two separate equations, and you can combine them and solve out for up to two unknowns. So the two unknowns you can solve for are V1 final and V2 final. The problem is it's kind of a lot of algebra. It's usually takes a couple of pages to do this, and you get a little tired. Anyway, this is the answer. So you can just sort of look at it. So V1 final, it's related to the masses, which are known, presumably. M1 minus M2 over M1 plus M2 times V1 initial. Remember, V2 initial was 0, because you assumed it was at rest. And then V2 final is just this different equation. So I don't really expect you to do all the algebra to derive this, but basically this is something that I will put on the first page of the, or maybe page 2 of the midterm. Under this possibly helpful information, I usually put little equations there. And this is just the simple equation for a head-on elastic collision in which ball 2 is initially at rest. You always get these final speeds. So example, let's do a demonstration. If you've got a 0.5 kilogram basketball and a 0.05 kilogram tennis ball and you stack them on top of each other, drop them from some height, how high does the tennis ball bounce? Didn't bring my meter stick, but this is one of those demonstrations in which the first couple rows of laptops are in a certain amount of danger. I'm going to try. So this is maybe 0.82 meters, maybe above this. Let's see what happens here. Above the table. Whoa. Okay, so it's sort of magical. You'd expect if you drop something, it will come up to, at the most, the same height from which it is dropped. That's assuming if it was an elastic collision. Thank you very much. If it's in a perfectly elastic collision, then with the floor, how does that conserve momentum? Wait a second. The momentum is reversed because there's an external force. The whole rest of the Earth is pressing on the table, right? So I guess maybe there's... Anyway, so what happens really when you collide with an object that has infinite mass is that momentum is not conserved, it just flips, but kinetic energy is conserved before and after. So whatever speed it hits the floor with, it then leaves the floor at that same speed, and so it should reach up to the same height. But it doesn't because it's not perfectly, it's an inelastic collision. So how can we solve out for how fast the tennis ball is going at the end? And let's assume all perfectly elastic collisions. Segment 1 is that you've got free fall of both balls as they fall. And then you know they're going to hit the floor with some certain speed. Should be easy to find. You can use energy or something. And then, this is the tricky part. The only way I've been able to solve this is if I kind of imagine that as they're falling together, there's a tiny little gap between the tennis ball and the basketball. So then the basketball first hits the floor and reverses its direction. That's like segment 2. And then, like just a really instant later, it then hits the tennis ball. And that segment 3, that tennis ball, basketball collision with the basketball going up and the tennis ball going down is the one we're going to use that equation for. Because we're going to get V2 final, and we'll see how high it goes. So the first, I'm not even going to do, basically, if you drop something from a height of 0.82 meters, you use conservation of energy. Kinetic energy initial equals, plus UG initial equals kinetic energy final plus UG final. So this is how fast do the balls go just before they hit the ground, square root. It's going down, so it's negative 4 meters per second if you define positive y as up for both of the balls. And then, remember, the basketball collides elastically with the table. So it was going down negative 4 meters per second. Then it's going up with plus 4 meters per second. Can you picture that? And somehow that happens before it hits the tennis ball, because there's a little gap. So now we have the collision that we're waiting for with that equation, which is that a 0.5 kilogram basketball moving upwards at 4 meters per second strikes a tennis ball, 0.05 kilograms, initially moving downward. What time is it? Okay, we're good. Their collision is perfectly elastic. What is the speed of the tennis ball immediately after the collision? No problem. Because it's on the first page is this equation. So what you've got, you can kind of do this initial. You've got 2. So 2 is going to be the tennis ball. And 1 will be the basketball. So 2 is going down. V2 initial is -4. And 1 is going up. Sorry, it's a head-on. V1 initial is +4. Okay? And then finally, what's happening is that you've got this V2 final is going way up. And this is what we want to find. Okay? So what I'm going to do is let's go to tennis ball reference frame just before it hits the ground, where it's at rest. To do this, what I'm going to do is I'm going to add +4 meters per second to all the velocities, to the y velocities. And then, remember, at the end, to switch back to the lab frame by subtracting off those +4s, for subtracting the 4 meters per second to lab frame by subtracting the 4 meters per second. So that's my strategy. We're going to use V2 final. So I guess what we'll get, is V2 initial prime is 0, and V1 initial prime is +8. Oops, thank you. Meters per second. So V2 final is equal to 2 m1 over m1 plus m2. Can everybody hear? V1 initial prime. The mass of the basketball is 0.5. And you've got 0.5 plus 0.05 times 8. I get plus 14.5 meters per second. That's in this prime frame, the rest frame of the tennis ball. Then I'm going to subtract that 4, and I get V2 final is plus 10.5 meters per second in lab frame. And then we can use conservation of energy and find that it's going up to 5.6 meters up. Goodbye. I'll see you Wednesday.